Hey everyone. Just gonna give it another minute just to let people um, trickle in, and we can get started. All right, I think we can probably get started. Thank you everyone for joining. My name is Josh Hannon, and I'm from the team, the Flow blockchain team. And I'm here to give an introduction to smart contract programming with our programming language called Cadence. And let's just get started. Um, so after this presentation, we kind of have a few outcomes. We want you to understand the flow programming model, and how to use the some of the like tools for beginners for learning how to use flow and cadence, and basically understand the kind of fundamentals of smart contracts built with cadence, including some basic NFT code, and where to go to find more information. So I want to start from a high level, to just remind everyone that in the course of the history of technology, every time there's a new software domain, a new evolution in technology, there is almost always a new programming paradigm that emerges for that software domain. So, for example, commodity hardware introduced portable code, relational databases, had atomic transactions, graphical UX, object-oriented programming, and so on and so forth. And now that we have these digital assets that we're using blockchains for, smart contracts have emerged as the new programming paradigm. And just to kind of remind everyone the basics of smart contracts. A smart contract is a piece of code that lives on chain in an account, that is public and whose code can be executed by anyone on the network or by any other smart contract. And the code execution can only be initiated by external actors. And the reason why people would want to use smart contracts is for primarily for transparency. It's this public blockchain that everyone can see all the code on. You want everyone to be able to verify that the code is running as intended, and you don't want it to be proprietary. Additionally, since it's on this public network, you want your code to be able to be interoperable with anyone else's code. You want them to be able to take your project and build interesting things on it, without having to worry about you revoking access to it, or introducing breaking changes that could break their project that they've built their business on. And that kind of goes along with this autonomous execution and trustless environment. You want to be able to trust that the code is going to run as written, and not have to worry about any third parties that might want to interfere with it or change it in some way. So now that we kind of like know about this smart contract programming paradigm, we also need to acknowledge that every time there's been a new programming paradigm, there's been new languages to support it. So portable code had Fortran, atomic transactions had SQL, object-oriented programming had Smalltalk and Java, and then client-side scripting has JavaScript. With in the blockchain domain, there's with digital assets, there's some important things to consider when building these smart contracts. The two main aspects of digital assets that we kind of like to boil this down to is managing the assets and controlling access to the assets. So that's like knowing how to like move them around in accounts, and also knowing who is allowed to move these assets around, or access them in some privileged way. And until recently, in general purpose languages, these scarce resources are represented by regular data structures. So like money might just be represented as a entry on a ledger in a database somewhere, or like a collectible might just be a regular data structure that is stored in a smart contract. And we discovered that that traditional data structures don't fully satisfy the requirements that we want to enforce for digital assets, because as we know, digital assets, they have a lot of value. The fact that they're on this public network, where all the code is public, means that any little code bug or anything can be easily exploitable by malicious actors, as we've seen in many other blockchains and programming languages like Solidity, which represent digital assets with regular data structures. So we've created a table here that kind of illustrates the problem with using regular data structures. They're easy to create, they're easy to copy, and they're easy to delete and destroy. Whereas with scarce assets, you want them to be carefully controlled. You want the creation of them to be carefully controlled, and you don't want to be able to copy them. And you want people to be very deliberate about when they destroy these assets, because they have value, and we don't want people to just lose them or accidentally destroy them. And that's why with Cadence, we are introducing linear types to the blockchain programming environment. Linear types is a programming paradigm that's been around for a while, mostly in research papers and just kind of proof of concept languages. But linear types are a programming language construct that is similar to a data structure, but has much more strict rules about how they can be used and how they can be created. And for example, we've showed here on this table, in relation to regular data structures, the linear types line up with the requirements that we want for scarce assets a lot better than data structures do. They have to be carefully controlled. They can't be copied, and destruction has to be deliberate, with a specific destroy operation that you call on them, instead of just losing access to them. And so in Cadence, we call these linear types resources. And the way that we enforce these requirements is that we require that only the contract that defines the resource is allowed to create it. And then the language itself is a very strongly typed language that has strong runtime support for preventing these resources from being copied, or accidentally lost or deleted, so that it can be a true representation of a digital asset. a true representation of something that has value and that needs to be controlled from a security standpoint, so we don't lose them with just kind of unintentional mistakes like human mistakes or software bugs or things like that. And so um, that's where Cadence comes in. We Cadence is the smart contract language that is used on the Flow blockchain. Um, from the very beginning, we designed Cadence for specifically for Web3. Um, like I mentioned before, we have this resource-oriented programming paradigm that we've built, where assets, instead of being stored in as just an entry in a ledger on a single like central smart contract, assets are actual language objects that are stored directly in the account of the owner, of the account that owns them, um, and is and can be directly controlled by that account, and moved, like actually moved, from account to account when they're being transferred. Um, this has a lot of benefits for security. One being that it's an even more decentralized version of the currency or of assets, because now that the balances aren't stored on a centralized ledger or a centralized contract anymore, it's much harder for malicious actors to hack them, because instead of hacking a single account, they'd have to hack every single account individually that owns these assets. Um, additionally, there are some um, there are some more subtle language improvements that we've introduced to Cadence over compared to like Solidity or other smart contract programming languages, like not having integer overflow by default, having a very strong static type system that prevents developers from introducing any undesirable program behavior or mistakes before they even start executing their code. So it just makes it so much easier for developers to avoid common mistakes in smart contracts programming. And the Cadence language has always been and is still open source. The design of Cadence, the Cadence language and Cadence smart contracts makes building new apps that use other people's smart contracts much easier. Because of this resource-oriented programming paradigm, it opens up the possibilities for how projects can interoperate with each other and build on top of each other in really interesting ways, which I hope you'll see later in the presentation. And the syntax of Cadence is familiar to a lot of different developers. It's kind of a it's kind of similar to TypeScript or Swift and Kotlin. We've taken some inspiration from Rust as well. It should be very easy to pick up. And we know that it's very easy to pick up because there's thousands of developers already on Flow who have picked it up and are having a great time with it. Actually, I want to stop for a second and just ask if anyone has any quick questions before we move on to looking at some actual Cadence code. I see one here. Does Cadence support algebraic data types like in Haskell and Rust? Does it support pattern matching? That's a good question. I don't know the exact answer for that. So we might be good. We have a Flow Discord that's linked on our website, flow.com. So you can if you join the Discord, you can ask in the developer forum channel there, and you should be able to get some answers. Then the next question: are any Chainlink services available on Flow? As far as I know, there isn't a direct Chainlink integration on Flow yet, but it's something that that we're working on. And I think for the purposes of the Chainlink hackathon, um, it's something that you can still build into your smart contract, like as if there was a Chainlink service there, even though it might not be like fully accessible right now. But you'd probably need to talk to the Chainlink organizers to see what the specific requirements are there. So Cadence, somebody asked if Cadence has a compiler. Cadence currently is an interpreted language. So there currently is not a compiler for Cadence, but the Cadence team is working on a compiler that they're hoping to be able to introduce sometime in the future to have better performance for Cadence smart contracts. But just for kind of quick development, quick iteration on the language, we started out with just an interpreter for now. And yeah, I'm not sure about the Chainlink price feed. Also, you'll need to ask the Chainlink hackathon organizers. So we'll move on to the next slide, and we can start looking at some code. So I just want to give a quick glimpse of Cadence right now. So in this slide, we've kind of just declared the most basic representation of an NFT contract that you could have in Cadence. So as I said before, these digital assets are represented by resource types, and a resource type is kind of like a regular data structure. It's a composite type that can have any number of fields and functions that can interact with those fields. But the rules for resources, unlike structs, are that they can only be created by the contract that defines them. They can't be copied, and they can't be unintentionally lost. So, and what I mean by that is like during like a function execution, if you create a regular struct and you reach the end of a function execution, a normal language will usually just garbage collect that. It'll just deallocate the memory that was allocated for a struct, and that'll get lost at the end of the function execution. With a resource, if you don't explicitly handle the resource at the end of the execution of a function, then the language will throw a type checking error that says there's a loss of resource here, and you need to handle it. So that means explicitly returning the resource from the function, explicitly sending it somewhere else, but handling it in some way so that you always know where these assets are going to be at the end of the execution of a transaction or of a function. So in this contract, this NFT is declared as this resource, and right now it just has an ID. But for further complexity, you could add metadata or other things like that. And then the function defines a create NFT method for people to just create an NFT that they want. Now, this contract is not a like actual production contract that you'd want to use in real life, because obviously you wouldn't want everyone to be able to create as many NFTs as they wanted to. But it just kind of illustrates the kind of like basics of the language. And then at the bottom of this, we have this init method that's declared in the contract, where it starts to introduce some of the account API in Cadence, where we're actually saving a copy of, or not a copy, saving a created NFT object directly in the account where the contract is deployed to this storage path. So it's illustrating that these assets are actual objects that are stored in an account. And so if the owner of this wanted to transfer an NFT to somebody else, they would actually remove the NFT from their account and then store it and then send it to somebody else's account. So it kind of gives you a little more of a kind of tangible feel for how these assets work. It's as if you were taking like a dollar bill directly out of your physical wallet and handing it to somebody else, and they were putting it into their wallet instead of just updating a number on a ledger somewhere. There's a couple other questions I want to answer quickly. So somebody asked if there's a way to deploy Cadence using code. So Cadence contracts the code is actually deployed directly on chain and then executed by the Cadence compiler. So like when you query smart accounts on Cadence, you'll actually get the contract code, unlike Solidity where you just get like the bytecode. And you can deploy that on any network. And then somebody asked where the URI for the NFT is in this flow contract. So like I said, this is just a basic NFT contract. It's not something you would actually use in production. So in a production contract, NFTs have a lot more metadata that's used to represent different aspects of it. So I want to kind of talk about, like, back up a little bit and talk about the account model in Cadence and in Flow. So each user of Flow is represented by an account that is controlled by one or more private keys. So multi-sig constructs are built into Flow by default. Instead of having to use special multi-sig contracts, you can have any number of private keys on your account that you want, and you can add and remove them. So you can use any sort of multi-sig scheme that you want. Additionally, all state, meaning like all like data that is defined by contracts, and all of the interface to that state, meaning how you interact with it, are stored in accounts. And there's only one account type in Flow. Unlike something like Ethereum, where there are like the external accounts and the contract accounts, there is only a single account type in Flow. So in a given account, there's like can be contracts deployed to it, and there can be assets stored in that account's storage. So I'm giving a slightly more detailed look at an account here. So each account has a contract section where they can have any number of contracts deployed to it that define, like fields or structs or resources. And then each account also has a storage section where they store various things that are related to the contracts that are deployed on their account or on other accounts. So the main area is the storage area, and these are represented by paths, kind of like a file system. And the storage area is where you store your actual resource objects, which are the digital assets that you store in your account. Resource is represented by this @ symbol that we have next to it. So in the storage section, we have the path storage /bar, where we store the type foo.bar, or store the resource foo.bar. Additionally, we have these public and private sections of your account. So the storage section of your account is only accessible by you, only accessible by someone who has signed the transaction with the key that controls that account. So it's completely private and nobody else can access it. But sometimes you want to give access to other people, or you want to make parts of it publicly accessible. So that's what the public and private sections are for. The public section is kind of like your account's like public API. Through something called capability security, which I'll explain a little bit more later, you can create links to your private stored objects in the storage section of your account. Um, you create those links in the public section, but you can use some of the language constructs to restrict those public links to only the parts of it that you want to to actually be publicly accessible. So for example, if you have an NFT stored in your account, obviously you don't want people to be able to withdraw that from your account, but you might want to give people access to reading the metadata of that NFT. Um, or you want to give people public access to deposit new NFTs into your account. So that's what you would put in the public section. This public interface that only contains like the metadata parts and the deposit parts of your NFT. Additionally, private it's similar to public in that it's kind of like this like linking API, but for private that's still only accessible by you. But you can give the links that are created in this private section to other accounts who you want to have kind of like restricted access, but not public access. So I hope that wasn't too confusing. The capability part of Cadence is definitely has a little bit of a learning curve, but it's one of the most powerful features of Cadence's security model and access control model that opens up a lot of possibilities with how you can control access. And I'll explain a little bit more about it later. So as we've explained earlier, any sort of computation on the blockchain has to be initiated by a transaction, and that applies to most smart contract programming environments and most blockchains. Um, and Transactions are always signed by an account and can access the account's private storage and private deployed contract code. Um, and additionally, they can access any public contracts or public interfaces like those public APIs that I talked about earlier that are stored in other accounts. But the unique thing about transactions on Flow is that transactions can contain any arbitrary amount of code. So unlike something like Ethereum, where a transaction is simply a single function call, on Flow, you can do basically anything you want in a transaction, any number of operations that you want. And that's kind of because of the programming paradigm in Cadence. Since we have since kind of like the ownership of assets is managed in this much more decentralized way, transactions have to be able to do multiple operations in a single transaction, because, for example, they have to um, like withdraw an NFT from an account and then deposit it to another account in order to transfer it, or if they're like performing a sale, they can like withdraw an NFT from their account, put it up for sale in another account, and do any number of these things. And it's really nice because that way transactions are completely atomic. They all get executed sequentially in one go, so that you can be sure that if you have a lot of things you need to do, you can pack them all in one transaction and not worry about any other accounts like jumping in the middle of the execution, take advantage of some like state that's like out of sync. So that definitely creates a lot of a lot of power with how you can how you can manage your assets, manage your accounts efficiently without having to run multiple transactions. Um, so so as it is with other languages, I'm just showing here that like an account might have a contract deployed to it with fields and functions. So if you want to call a function on that in that contract, you would sign a transaction that can like call the change number function, or you can like read that number with a different transaction and do whatever you want with it. So I want to give a quick introduction to the Flow Playground. The Flow Playground is a browser IDE that uses Cadence and uses a similar like paradigm to how Flow accounts are organized, to allow users to kind of get up to speed on Cadence quickly and learn the basics, do some prototyping with some ideas, and just like get comfortable with Cadence. And it also links to some tutorials where you can get a little bit deeper into some of the language concepts. So in the playground, we have a few sections. So primarily, we have the main code window of the IDE where you can actually make changes to code. On the left side of the screen, we have contracts, transactions, and scripts. So by default, there's 5 accounts that you can interact with in a playground environment. So when you click on an account, it'll show the different contracts that you can deploy to an account. So here we have just this basic NFT contract that we can deploy to the default account, and that is like the one I showed you that has like the ID and the metadata. And if we were to click deploy, that would deploy that contract to the account, and then here it shows that basic NFT is deployed. At that point, we can click on a transaction, and we can type anything into the transaction we want to interact with the contract in that account. So if I wanted to like create an NFT, I'd import the basic NFT from account 1. Then I would say let NFT. Let is simply defines a constant, and I can call the create NFT function to create an NFT and return it to the context of the transaction. This arrow is called a move operator, and it's used with resources to indicate that you're moving a resource from one location to another location. So here I'm creating the NFT with this create NFT method, and then it's actually moving that from the basic NFT contract to the context of this transaction. So now the NFT is kind of like in this transaction, but because I don't do anything else with the NFT in this transaction, it's showing me this error message that says loss of resource. So that's saying if I were to execute this transaction, it wouldn't know what to do with this NFT because it's been moved out of the NFT contract, but I don't do anything with it. And the language doesn't like that because, as I said before, it's a digital asset. It needs to know what to do with this asset so it's not lost. So there's various things I could do. The easiest is to just destroy it. This is where the explicit destruction comes in. I have to explicitly call destroy on something to destroy it. But if I wanted to store it in my account, that's where I would access my account via this argument here, this account object. So I could just do account.save NFT to a storage path. So now that I'm storing it in my account, there's no more error because it knows that the NFT has been handled. It's been put into a safe place, and then I can send it, and it it saves the NFT in my account. So now I know it's there. Um, Additionally, scripts can be used to just query data. Scripts are read only, so they can't actually modify any state, but they don't require a signature or anything because they're not modifying anything. But they can read any publicly accessible information. Um, they can read any publicly accessible information on accounts or contracts. Though actually, we introduced a feature recently that scripts actually can read any private information too, because as we all know, everything on a blockchain is public anyway, even if it says private in the code. And so a nice thing with scripts is that even if something's private, you can still access it. So it's a great way to if you want to test a transaction um, uh, without actually modifying any state, you can test it via a script or read private information because you're not actually modifying any of it. And it's been super useful for a lot of us on Flow. Um, Somebody asked, can I deploy to mainnet from the playground? Currently, you can't deploy to any of the public networks on the playground. The playground just uses the emulator, which is just our kind of local net. So when you create a playground project, it starts an emulator for you that just contains your local contracts um, and state, and you just kind of interact with that on the playground. But it would be really nice to be able to deploy on mainnet. And I think that's something that the playground team wants to be able to integrate soon. But not sure what the timeline is on that. But we also have a command line interface that is easy to use, that allows you to do deployments on testnet and mainnet. And there are many uh, SDKs for JavaScript and Go and other languages that are maintained by the community that you can use for more fine-grained control over deployments and transactions. So yeah, that's the playground. We have some links to tutorials. So there's Hello World, fungible tokens, non-fungible tokens, all these that'll go into more detail of how to define those contracts and work with them. But I will move on to the next slide. So I want to give a quick example of the actual how NFTs are actually defined in production with the Flow NFT standard. So this is equivalent to ERC 721 or ERC 1155 on Ethereum. In that it defines how non-fungible tokens should work in Cadence. So I'm just going to walk through this. I'm going to just walk through this real quickly. So I might miss some things that are confusing, but we are running out of time, so I can't go take too long. Yeah, so the non-fungible token is a contract interface. So it basically says that any contract that wants to implement a non-fungible token has to implement this contract interface. So that is shown by this example NFT. It implements the non-fungible token interface, and that kind of enforces various requirements that non-fungible tokens need to follow. So it requires a total supply field that just indicates the number of NFTs of this type that are in existence. And then it defines common events that NFT contracts should admit when they're withdrawn or deposited to accounts. Then it defines the resource, the NFT resource that has to implement this INFT interface. This provides these methods that are These methods relate to NFT metadata. So we don't really have any requirements for how NFTs store metadata. They can store it however they want or make it however complex they want. But there are standard ways that an NFT can like return information about the metadata that it stores, and those are called views. And this allows NFTs to return information about their metadata in standardized ways, so that there are ways like third-party apps or third-party smart contracts can be able to read and understand an NFT's metadata in a standardized way so that they can display it on their website or interact with it in a smart contract without having to like understand like some proprietary metadata organization that a project might have defined, and that really allows the kind of third-party interoperability and composability to be much easier on Flow than it is in some other languages. So additionally, I'm gonna come back to these in a second, but additionally in Flow, the non-fungible token standard defines this collection resource. So we said that the asset itself, the NFT, is a resource, but it's nice to have a way to easily manage your whole collection of NFTs. So the collection resource is acts as like a place where all your NFTs of a single type can be stored, so that you can easily like withdraw them, easily deposit them, and get information about them. So the collection resource defines a field that stores the NFTs in the collection. And then it defines withdraw and deposit methods so you can move them in and out, and then methods to get a list of IDs that you own, and like borrow reference to them so you can read metadata from the NFTs. And then it just defines a function to create an empty collection so that when you, as a user, want to store these NFTs in your account, you create an empty collection, you store it in your account, and then you can start owning these NFTs. So that's basically it for the non-fungible token standard. There's also these resource interfaces that the collection implements, and that relates to those the capability security that I talked about earlier, like that public account API that you have on your account. When you want to, if you like have a collection in your account and you want people to be able to deposit new NFTs to it or read information about it, you use this collection public interface to say that in my account, I want the deposit, get IDs, borrow NFT, and borrow NFT safe methods to be publicly accessible. So I'm going to create this link that is typed as collection public to say that publicly only these methods can be accessed. And then, but as you can see, with the withdraw method is not included in this public interface. So withdraw is not publicly accessible as it should be. But we still have this provider interface to say that like if you have a friend that you want to be able to withdraw NFTs from your account without needing to ask you for permission every single time, you could give them a link that is a provider to say that they can withdraw these, but only they can, because they're the only one who owns this provider link. And that kind of is like the power of capabilities. Capabilities are a way of enforcing access control based on what you own instead of who you are. So in the Ethereum world, in order to do anything privileged, any sort of like private like authorization, Contracts will often check who the initiator of the transaction is. So it'll check like message.sender, and it'll say if message.sender equals like this address who that the contract has deemed to be like the owner or like some authorized address, then they're allowed to perform this privileged operation. Whereas on Flow, there's no such thing as message.sender, because on Flow it doesn't matter who you are. It doesn't matter your account address. Doesn't matter as much. What matters is what you own. So um, it's kind of like if I were to give a real world analogy, it's as if like the message.sender paradigm is like if you were to get like a retinal scan or like a fingerprint scan to access something. Whereas on Flow, it's more like if um, you have like a key card that or like a device that like you have to hold in your hand and like press a button on to access something. Um, and what's good about that is that since the access to the privileged functionality is contained only in this object, um, it's much harder for malicious actors to exploit, um, because they can't even like see that object. Like on Ethereum, anyone can call these like public like privileged functions that check message.sender. Like anyone can call it. I mean, most of the time they're not going to get to do anything. But if there's any sort of bug in that access control logic that checks like the owners or checks things, um, malicious actors can figure that out and call it. Whereas if there's a bug in this privileged function on Flow, malicious actors can't even access it to try to exploit that bug because that function is not publicly accessible. It's only accessible by the person who owns the object that controls it. So it just provides another layer of security for developers to be sure that any bugs aren't going to be exploited. Um, and that's kind of like what this illustrates here, that your NFT collection stored in your account, is this whole red box here, that contains like everything, like, but only the things that you've deemed you want to be public are accessible by the public, which includes those like get IDs, deposit, borrow NFT, um, through this public link. And yeah, and I talked briefly earlier about metadata, the Flow NFT metadata standard. Um, so, but I can go over it again. But like we have it's the standard. It standardizes how metadata is retrieved, not how it is stored. So it gives projects a lot of flexibility to store their metadata, but they have a standardized way um, of sharing it with other projects so that it can make interoperability much easier. We've got a lot of standard views that are already defined, like just a standard display view, any URLs, data about your collection, how it should be displayed on websites, any royalties that you want to enforce, traits about NFTs, and even more. And we're still adding them. Like currently we're working on a license metadata view that defines like rights for NFT holders. We're working on views to represent like booster packs for NFTs. So there's a lot more in the works, and you can even define your own custom views that are specific to your project if you want that to be more easily accessible. Um, and I think, yeah, we have about 10 minutes left. So I want to give some time for questions, but um, I just want to remind people that there's a lot of ways you can get plugged into the Flow community and in the Cadence community. The main portal for developers is developers.flow.com. That has links to all the tutorials and reference docs for Flow and for Cadence. including like the full language reference for Cadence, docs for how to use the CLI. And then we also encourage you to join the Flow Discord. There's links for the Flow Discord on flow.com and on the developer portal. Join there, introduce yourself, ask questions. We also have a Cadence tag on Stack Overflow that we're trying to start using more. So if you have a Cadence question, you can just ask on Stack Overflow and add the Cadence tag to it, and someone will usually jump in and help you get that answered there. But yeah, I just want to see if anyone has any other questions. So Evan says, what browser dApps are currently live and open source that could be used as a reference when building on Flow? So yeah, there's actually a lot. So there's a website called Flowverse. Flowverse is a community built website that kind of explains all the projects that are currently building on Flow, or at least all the ones that they're aware of. So you can see everything that's built on Flow here, which ones are open source, which ones are not. Doodles is a big project that moved from Ethereum to Flow recently that we're excited about, and they're all open source. But this has lists of all of these projects that you can look at. Also, there's like NBA Top Shot, which is like one of the Dapper Labs created. Sports projects, all of that's open sourced. There's also a really good project called Find that is like a name service project for Flow. They've got some really good Cadence developers that have built a lot of really interesting contracts for what they work for. But you can find a lot of really good links to code that you can look at for examples on this. And then additionally, we also have some of the Flow repos, like the NFT repo has some examples. This is where like the actual like NFT standard that is used on mainnet is defined, but we also have an example NFT contract that if you wanted to, you could simply you could copy this contract and then obviously like change the name of it, change the metadata and things like that to make it specific to you. If you just wanted to really quickly get a working NFT contract for yourself. But yeah, if you just search around in there and in Flowverse, you'll see a lot of good examples that you can use. Emerald, another really good project to look at is Emerald. Emerald also makes a bunch of really good Cadence tutorials and like video tutorials and things like that you can follow to get deeper on some of the important Flow concepts. So they're another really great project to check out. But yeah, definitely get on Flowverse and join the Flow Discord. And if you want, or if you're looking for something specific, feel free to ask there, and we can help you find it. Anybody else have any questions before we wrap up? All right. Well, if that's it, yeah, we can probably finish up. Yeah, thank you for joining. It's always good to introduce Flow to more people. And excited to see what y'all build for the Chainlink Hackathon. And we're always happy to help. And the Flow community is always happy to help too. So definitely don't be afraid to get on Stack Overflow or Discord and ask some questions and say hello, and we'll give you some pointers. So thanks for joining, and good luck with your projects.